Hey guys, Mr. B here, and in this video we're going to be going through the practice problems in chapter 12.3 on limiting reactants and percent yield. And I'm going to be doing the problems here on quizzes just to make sure that I go through the exact same ones that you guys are going to see. So let's get started. Here we go. Now I have written these down on paper because I'm going to be doing my math work on paper, and I'll be switching to my desk cam here to do that. So, and I wrote them down in advance just so that way I didn't have to waste time writing them down. Okay, so our first one here, it says the equation for the complete combustion of ethane, C2H4, is given. If you begin with 2.70 moles of C2H4, how many moles of O2 will be needed to react with it? It says round your answer to 3 sig figs. Write out your math work. You will need it for problem 3. Okay, so let's switch over to the desk cam so that we can do this problem. And I need to turn my light on here. There we go. Okay, so like I said, I have written down the problem already. Okay, number 1. So we have 2.70 moles of C2H4. How many moles of O2 are needed? They're giving us a reaction, and I've written that down here. So we're going to start with 2.70 moles of C2H4, and we're basically converting moles of C2H4 into moles of O2. Okay, and to do that, we need to look at our chemical equation, and we need to look at the mole ratios between the two. So between C2H4 and O2, it is a 1:3 ratio. So for every 1 mole of C2H4, we're going to need 3 moles of O2. So I'm going to set up my conversion table like this. Since I'm starting with moles of C2H4, 1 mole of C2H4 will be written on the bottom of my fraction. 3 moles of O2 will be written on the top of my fraction. That way, moles of C2H4 cancel with each other. And we're basically just going to take 2.70 and multiply that by 3. So 2.70 times that by 3. And I get 8.1. And it does say, I think, to round to 3 significant figures. So we'll just say 8.10 moles of O2. All right. So let's go switch back to our quizzes. And let's put in 8.10 moles of O2 and submit. All right, cool. So there's the first one. All right, let's take then a look at number 2. So it looks like we have the same reaction. And it says if you begin with 6.30 moles of O2, how many moles of C2H2 will be needed to react with it? Okay, so again, let's switch back to our desk cam. And I have this one written out again already here. So if we have 6.30 moles of O2, how many moles of C2H2 will be needed? So it's pretty much the first problem, but instead of going from moles of C2H4 to moles of O2, we're now going from moles of O2 to moles of C2H4. Oh, I realize that there's a typo, so I will change that probably before you get to this video, but C2H4. Okay. Anyway, all right. So it's a 3-to-1 ratio, or 1:3. Okay, so it's the same conversion factor we used in problem 1, but the difference now is we're going to flip it. Okay, so since we're starting with moles of O2, we're going to have 3 moles of O2 on the bottom of our fraction and the 1 mole of C2H4 on the top of our fraction, like this. Okay, but it's pretty much the same exact problem as problem 1. Number 1, we're converting between the same 2 materials. So let's take 6.30 and we are going to divide that by 3 equals 2.1. And I believe, again, it says to round to 3 significant figures, so we'll just add a 0 on at the end to give it 3 sig figs. We got 2.10. All right, so let's go back to our quizzes. Type in 2.10, hit submit. Okay, here we go. So problem number 2 is finished. Okay, so now this one says, looks like we have the same reaction. It says if 2.70 moles of C2H4 is reacted with 6.3 moles of O2, the limiting reagent is the blank. It says refer to your math work from problems 1 and 2. All right, so let's take a look at our math work from problems 1 and 2 so we can figure this out. So we have 2.70 moles of C2H4. That's what we began with. And we need Okay, so let's make sure we understand that this is given. Okay, this was given. This is what we need in terms of O2. So we were given 2.70 moles of C2H4. We need 8.10 moles of O2 to react with that. Down here, we are given 6.30 moles of O2. And in order to react all of that O2, we need 2.10 moles of C2H4. Okay, so looking at what we're given for the C2H4 and what we need, or what we're given for the O2 and what we need, can we figure out which one is limiting? All right, well, I would say looking at this, the oxygen is what is limiting us. And here's how I know. We need 8.10 moles of O2. Okay, that's how much we need. But we are only being given 6.30. So we do not have enough. Okay, we need 8.10. We are being given 6.30. On the other end, for the C2H4, we need 2.10, but we're being given 2.70. So we have more than enough. Okay, we have more than we have more here that we're starting with than what we need, which ultimately means that the O2 is what is limiting. Okay, so limiting reactant is going to be the O2. Let's go back to our quizzes here, and let's just type in O2 for which limiting is the limiting reagent. Hit submit. There we go. All right, awesome. Okay, moving on to the next one. The heat from an acetylene torch is produced by burning acetylene, C2H2, and oxygen. Okay, so this now is a different reaction than we had in the previous ones. It says how many moles of O2 would be needed to fully react with 2.40 moles of C2H2. Round your answer to the nearest whole number. Write out your math work. You will need it for problem 6. All right, so we're going to need to write out our math work. Let's switch back to our desk cam. Again, I have the reaction written out here already for us, just to save us some time. So here's our reaction. How many moles of O2 do we need to react with 2.40 moles of C2H2? Okay, so we are starting with 2.40 moles of C2H2, and we are trying to convert that into moles of O2. All right, so we're going from moles of one material to moles of another material. To do that, we're going to need to look at the reaction, and the conversion factor is going to be between these two materials. Okay, it looks like it is a 2 to 5 ratio. So for every 2 moles of C2H2, we will need 5 moles of O2. Okay, so 2 moles to 5 moles. So let's set up a conversion table and do some dimensional analysis. Since I'm starting with moles of C2H2, 2 moles of C2H2 will be written down on the bottom. 5 moles of O2 will be written on the top. Okay, so that moles of C2H2 will cancel with moles of C2H2, like so. So then to get our answer here, we are going to take 2.40 times 5, divide by 2, and it looks like we get a nice whole number of 6. And I believe the question did say round your answer to the nearest whole number, which we have. So it looks like 6 is what we're looking for. So let's switch back to our quizzes. Let's type in 6, hit submit. All right, there we go. Awesome. All right, next one. How many moles of C2H2 will be needed to fully react with 7.40 moles of O2? And it looks like we have the same reaction from the previous problem. Okay, so again, let's switch back to our paper. I have it written already out for us. So same reaction. How many moles of C2H2 would be needed to react with 7.40 moles of O2? So it's like the previous problem, but now we're just going the other way around. So rather than starting with moles of C2H2 and getting moles of O2, we are starting with moles of O2 and we are getting moles of C2H2. So to go from moles of O2 to moles of C2H2, we're going to need to use, again, the balanced reaction to use our mole ratios. It is a 2 to 5 ratio or 5 to 2 ratio. So it's the same conversion factor that we used in this problem, but now we need to flip it. Since we're starting with moles of O2, 5 moles of O2 will be on the bottom. 2 moles of C2H2 will be on the top. So moles of O2 will cancel. And again, math-wise, we're going to take 7.40 times that by 2, divide that by 5. We get 2.96. And the question does say round your answer to 3 sig figs, which this has 3 significant figures. So 2.96, I think, is what we are looking for. So let's again switch back to our quizzes. Let's type in 2.96, hit enter. All right, there we go. We're on a roll. Okay. Same reaction. If 2.40 moles of C2H2 react with 7.40 moles of O2, limiting reagent will be. Refer to your math work from problems 4 and 5. All right, so this is basically like the first ones that we did where we are being asked which one is limiting. Okay, so we're going to look at, again, the numbers that we calculated. So again, the numbers here that we are starting with, which is if we have 2.40 moles of C2H2, okay, so this is what we're given, and 7.40 moles of O2, okay, this is what we're given. Over here, this is how much we need. So if we are starting with 2.40 moles of C2H2, we need 6 moles of O2 to react with all of it. Then looking down here, if we are being given 7.40 moles of O2, we need 2.96 moles of C2H2. All right, so now we just compare. All right, we are being given 2.40 moles of C2H2. We need 2.96 moles. All right, so I can already see right here that we do not have enough. We are being given 2.4. We need 2.96. This is not enough, which means the C2H2 is going to be our limiting reagent. Okay, so let's switch back to our quizzes. Let's type this in, C2H2, hit submit. There we go. Okay, moving on to the next one. The heat from an acetylene torch is produced. Okay, so it's the same reaction that we were just dealing with. But now it says, how many grams of water can be produced by the reaction of 2.40 moles of C2H2 with 7.40 moles of O2? It says begin with the amount of material that is the limiting reagent. Round your answer to the nearest whole number. Okay, so this is the same exact problem that we just had in the last 3. It's the same numbers to begin with and everything. But now they are asking us to determine how many grams of this product can we make if we are starting with this much C2H2 and this much O2. Okay, and it does say begin with the amount of material that is the limiting reagent. Well, based on our previous question we just answered, our limiting reagent was C2H2, which means that to begin this problem, we are going to begin with this amount of material. So we're basically going to be starting with 2.40 moles of C2H2, and we are going to convert that into grams of H2O. Okay, so we're going to convert this into grams of H2O. Now, this is very similar to the problems we did previously, but now instead of going from C2H2 to O2, we're going from C2H2 to H2O. So first step is we're going to go from moles of C2H2 to moles of H2O. Okay? Remember that in order to go from one material to another in a reaction, we need to use the mole ratios that are being given to us in this reaction. And in this case, it's a 2 to 2 or 1 to 1 ratio. So technically, I don't even need to do this math out, but I'm going to do it anyway. For every 2 moles of C2H2, we will make 2 moles of H2O. Since I'm starting with moles of C2H2, the 2 moles of C2H2 from the reaction will be written on the bottom, so it cancels. And the 2 moles of H2O will be written on the top, okay, like this. Now, we're basically going to take this number times 2 divide by 2, which pretty much isn't going to do anything. So I'm not even going to pull a calculator out to do this because I can already tell you that the number that we are starting with is going to be the exact same number over here. Okay, 2.40 moles of H2O. So if we start with 2.40 moles of C2H2, we will make the exact same amount of moles of H2O, 2.40. But the problem is asking for grams. So basically, we just need to take this 2.40 moles of H2O and just convert it into grams. Okay? And to do that, we are going to need to know the molar mass of H2O. Okay. So we're going to need to pull out a periodic table, which I have mine right here. And hydrogen has a molar mass of 1. Okay, so H2 is basically 1 gram times that by 2, because there are 2 of them, so 2 grams. And then O is 16 grams. Okay, so O is 16 grams. If you add those together, the molar mass of H2O is basically about 18 grams per mole. So 18 grams of H2O per 1 mole of H2O. Okay, now again, this is something that we have learned before. Okay, all we're doing here is we're just converting moles of one material into grams. This is basically just a conversion that we've learned already using molar mass. So if you don't remember how to get molar mass, that just comes with practice and stuff. So since we're starting with moles of H2O, the 1 mole of H2O will be written on the bottom of our fraction. The 18 grams of H2O will be written on at the top of our fraction like this. That way our moles of H2O cancel. And we are going to basically take 2.40. So 2.40 times 18. We get 43.2. And the problem says round your answer to the nearest whole number. So I'm going to round this to 43 grams of H2O. Okay, so let's go switch back to our quizzes here and let us type in 43 and hit submit. And there we go, we got it. Awesome. Okay, question next one. So it says when 84.8 grams of iron 3 oxide reacts with an excess of carbon monoxide, iron is produced. Okay, and they give us a reaction. What is the theoretical yield of iron? Okay, so I'm going to switch back to my camera on my desk so we can show our math work on paper. And I do have the problem written out here. Okay, so here's our reaction. And the question basically is just saying, what is the theoretical yield of iron? Okay. And I forgot to write down, we have 84.8 grams of iron 3 oxide. Okay, so this is the material we are starting with. All right, so we are basically going to go from grams of this material, okay, 84.8 grams of this material, and they want to know what's the theoretical yield of iron. So basically they're saying if you're starting with this many grams of this material, how many grams of this material can you make? Okay, theoretically, like calculate it out, how much should you be able to make? So this is pretty much no different than the problems we've done in Chapter 12, Section 2. We're basically going to go from grams of Fe2O3 to grams of iron. But in order to do that, we, of course, need to get into moles first. That's always the first step. So step 1 is always going to be convert to moles. Okay, so convert to moles. So we'll take our 84.8 grams of Fe2O3, and we're going to convert that into moles of Fe2O3. We're, of course, going to need to know molar mass in order to do this calculation, because if we're going from grams to moles, that is the molar mass conversion. So let's pull up a periodic table here. Let's add together some numbers. So Fe iron is 56 grams. And we're going to times that by 2 because there are 2 of them in this compound. Okay, so 56 times 2, that is 112 grams. And then we have oxygen, and oxygen is 16 grams. But we're going to times it by 3 because there are 3 of them. So 16 times 3 is 48 grams. And then if we add those together, we get a molar mass of 160 grams per mole. All right, so here's our conversion factor. Okay, so there's our conversion factor. Here's what we're starting with. So 84.8 grams of iron 3 oxide. We're trying to get to moles of iron 3 oxide. Since we're starting with grams, the 160 grams needs to be on the bottom of our fraction, like this. And the 1 mole needs to be on the top of our fraction. Okay, this way, grams of iron 3 oxide cancel with each other. So on a calculator, we're going to take 84.8 and divide that by 160. Okay, so we get 0.53 moles of Fe2O3. Okay, so we now have moles. Here's our moles. All right, so again, step 1 was to take our grams of this material, convert it to moles, which we just did. Step 2 now is we're going to go from moles of this material to moles of this material. Okay, and to do that, so we're going to convert moles of Fe2O3 to moles of Fe. Okay, to go from moles of one thing to moles of another, we have to use the molar ratios or the balanced equation. So this is a 1 to 2 ratio. So 0.53 moles of Fe2O3. Over here, we're going to end up in moles of iron. And for every 1 mole of this material, we need double the amount of iron, okay, 2 moles. So if we set up our conversion table, for every 1 mole of Fe2O3, since we're starting with moles of Fe2O3, the 1 mole of Fe2O3 will be on the bottom. We're going to need 2 moles of iron. That's going to be on the top. Okay, that way our moles of iron cancel. All right, so we're going to take 0.53 times that by 2. So we get 1.06 moles of iron. And then lastly, since they want a theoretical yield and they're giving us a number that's starting in grams, they probably want this to be in grams too. So last thing here is we want to convert moles of Fe into grams of Fe. Okay, that's the last thing. So convert these moles into grams. All right. And I don't know why I keep switching colors. I apologize if this is annoying you. I just like to differentiate sometimes. Okay, so 1.06 moles of Fe. We're going to convert that into grams of Fe. So to do this, okay, to go from moles to grams, we're going to need to use molar mass like we did up here. So we'll need to know the molar mass of iron, which we actually have written right here because we had to use it to calculate the other one. So 56 grams per mole is the molar mass. Since we're starting with moles of iron, 1 mole of iron will be on the bottom, and 56 grams of Fe will be on the top. Okay, that way moles of Fe cancel. We're going to take 1.06 and times that by 56 equals 59.36, and it does say to round to 3 significant figures, so we'll say 59.4 grams of iron. That is the theoretical yield. Okay, so if we are starting with 84.8 grams of this material, theoretically, okay, based on calculations, this is the amount of iron that we should be able to make, 59.4 grams. So let's switch back to our quizzes. Let's put this in our answer. So 59.4, hit submit. Awesome, we got it. All right, so I believe this is the last problem. And it's a whole new reaction. Okay, so it says if 50 grams of silicon dioxide is heated with an excess of carbon, 27.9 grams of silicon carbide is produced. They give us our chemical equation. What is the percent yield of this reaction? All right, so let's switch back to our paper one last time. I have this already written out for us. Okay, so here's our reaction. And we have 50 grams of silicon dioxide. Okay, so that is this material, okay, 50 grams of this material. So if we have 50 grams of this, we heat it with the carbon, okay, they don't tell us how much carbon we have. We make 27.9 grams of silicon carbide. So 27.9 grams of this material is made. What is the percent yield? All right, so you might be thinking like, what am I supposed to do here? It looks like they're already giving us amounts of stuff. All right, so the main thing we need to realize is we are starting with 50 grams of this material. They're telling us that in a lab, Someone took 50 grams of this, they combined it, reacted it with carbon, and they made 27.9 grams of this material. This number here is an actual yield. This is like what someone actually got when they went in the lab and did this. However, theoretically, if we were to calculate it, if we started with 50 grams of this material and we calculated it, how much of this should we be able to make? Okay, they actually made this much, but in theory, maybe we should have been able to make more. So what we're going to do here is basically we're going to go grams of this material to grams of this material. And the grams that we're going to get, that we're going to calculate, is going to be compared to the number they're giving us to begin with to find our percent yield. So step one, as always, is we want to take our 50 grams of this material that we're beginning with and convert it into moles. Okay, that's always going to be step one, convert to moles. Hopefully by this point, you've got this down. So we need to convert this into moles. To go from grams of anything to moles of anything, we will need to know the molar mass of this material. So we're going to need to pull out a periodic table. Take a look at some numbers. So we have silicon, which has a molar mass of about 28. So silicon is 28 grams. And then oxygen, which is 16 grams. But then we need to times that by 2 because we have 2 of them. So that's 32 grams. And then adding those together, okay, 28 plus 32, I get a nice even 60 grams of silicon dioxide per mole. Okay, so there is our molar mass of this material, 60 grams per mole. So we're going to convert our 50 grams we're beginning with into moles using our molar mass. Since we're starting with grams of silicon dioxide, the 60 grams of silicon dioxide needs to go on the bottom of our fraction. The 1 mole of silicon dioxide needs to go on the top of our fraction. That way grams of silicon dioxide cancel. Okay, like this. So on our calculator, we will take 50.0 divide by 60 equals, all right, so I get 0.83333 repeating or whatever. So I'm just going to maybe write like 4 of them. We'll do our rounding at the end, I guess, for this one. All right, so here's our moles of silicon dioxide. Okay, so that's moles of this starting material. Now we want to figure out, well, how much of this material can we make? So we're going to go from moles of this material to moles of this material. Okay, so step 2, again, just like in the previous ones, is moles of one material to moles of another. So to do that, and again, I don't know why I keep switching colors. It just sometimes helps me to see which numbers I'm working with. So we have this many moles of silicon dioxide. Okay. Now, the nice thing with this step is to go from moles of this to moles of this. Looking at this equation, it is a 1-to-1 ratio. Every 1 mole of silicon dioxide we start with, we will make 1 mole of silicon carbide. So it's going to be the exact same number. Okay. We actually don't need to do any math. So if this is how many moles of silicon dioxide we're making, or we're starting with, we're also going to be making the exact same amount of silicon carbide. So this is also going to be silicon carbide, okay, here. So I actually don't need to do any math because it's a 1-to-1 ratio, okay? Same number, same amount, so it'll be the same number. Now the last part is we need to get this into grams. Oh, I should have written moles here, just realized, sorry. Moles of silicon carbide, okay? We need to get this into grams because, again, they're telling us that the problem, someone did this and actually got 27.9 grams. But in order for us to determine their percent yield, we need to compare it to how much we should have got or what should have been able to get, and it's got to be in the same units. Okay, so we're going to take 0.83333 moles of silicon carbide, and we're going to convert that into grams of silicon carbide. Okay, so we can compare. So grams of silicon carbide. To do this, of course, we are going to need to know molar mass, just like here. To go from grams to moles, you need to know the molar mass of the material. So we're going to need to add some numbers. So silicon, we already have the molar mass for silicon. We've written it up above, so that's 28 grams. And carbon has a molar mass of 12 grams. Okay, I just know this off the top of my head. If you want to look on a periodic table though to find it, go ahead. So if we add these together, 28 plus 12, we find that the molar mass for silicon carbide is about 40 grams per mole. Okay, so here is, make sure we can see all this here too, I apologize, it's not off camera. So here is our molar mass. Seeing as we're starting with moles of silicon carbide, this is our molar mass. The 1 mole of silicon carbide is going to go down here on the bottom of our conversion. The 40 grams of silicon carbide is going to go on the top of our conversion. That way, moles of silicon carbide cancel with moles of silicon carbide. And we're going to take 0.83333, so 0.83333, and times this by 40 equals, we get 33.3332. So 33.3, I guess we'll just keep it at 3. That's fine. 33.3 grams. Okay, now this number we just calculated, this is our theoretical yield. Okay, so basically what this is saying is, if we start with 50 grams of this material, we should be able to make 33.3 grams. However, someone actually did this, and they only made 27.9 grams. So the question then, of course, is, what is the percent yield? Percent yield is kind of like percent error. To determine your percent yield, you're going to take your actual yield, divide that by your theoretical yield, and then times it by 100 to get it as a percentage. So our actual yield in this case was 27.9 grams. Okay, this is our actual yield, and this is the number that is given to us in the problem right here. Okay, so 27.9 grams. That's our actual yield. Our theoretical yield is the number we just calculated, 33.3 grams. That's how much we should have been able to make. Okay, and then we're going to times it by 100. So if we do on our calculator, 27.9, oh, my calculator's not in the frame, there you go, 27.9, divide this by 33.3, and then times 100, we get 83.78, blah, blah, blah. And the problem does say to round your answer to 3 significant figures. So we're going to say 83.78 would round to 8%, 83.8%. Okay, this is our percent yield. Okay, so obviously they did not get 100%, which you'll never get a 100% yield, but 83.8% isn't bad. So let's switch back to our quizzes one final time. Let's put our number that we just calculated in our box. So 83.8%, and let's hit submit. 83.7. Okay, that's just a rounding error. So 83.8, 83.7, depending on how you round. Either way, I would count that as a win. So, all right, guys. Hopefully that helps you with understanding how to do these problems. I know this video was long. I appreciate you taking the time to watch it and sticking it out with me to go through all these and really make sure that you know what you're doing. But again, as always, if you have any questions, you need any extra help, you just want some practice, I am always free. Just reach out to me so I can help you. All right, that's it for this one. I'll see you in the next one. Bye.